Okay, good morning. Please scan this QR code and just focus on the first two statements, okay? The last three are related to the quiz we've done last week, and we'll come back to those three later after we finish on the lecture material today. All good? Now, let's look at the first one together. So last week, we basically talked about model selection methods in choosing the optimal order for the AR model. And we look at AIC, BIC, and stepwise procedure to find this optimal order. So the first one here is related to BIC and AIC, discussed on Friday. So what it says is that lower BIC and AIC values in AR models mean that the model is simpler with fewer lag terms. So do you think this is a correct statement or it's a false one? Those who just came in, I give you 1 second in the code, okay? 5, 3, 2, time's up. Okay, so the majority gets it correct. So indeed, this is a false statement, okay? A lower BIC and AIC doesn't typically mean that the model is simpler. It just means that the model has a more balanced sort of weight between model complexity and the number of parameters. It's not necessary that the model with the fewest amount of lag will give you the lowest AIC or BIC, okay? Remember that both the BIC and AIC, they are a function of two terms. The first term is essentially the model, the model fit, which is given by the residual sum of squares. And obviously, the more parameters, the smaller the RSS, the smaller the first term, okay? So more parameters, a smaller first term. However, the second term of both information criteria grows linearly with the number of parameters, m. So the more parameters there are, the larger the penalty term, and the AIC, both the BIC and the AIC, they attempt to reach the balance of both terms, okay? So the first term goes down, whereas the second term goes up when the number of parameters increases, okay? So AIC and BIC are not necessarily minimized at the simplest model. And we can also see that here in the example with the growth model. So here we have that the AR2 is favored compared to the AR1. And in some other models, you might see that with a different data, the BIC or the AIC might actually favor, let's say, AR4 or AR5, just like the homework question, if you did attempt it. The homework question last week, okay, the optimal model is actually the AR4 chosen by the smallest BIC, okay? So they are not necessarily slower with simpler models. So this is a false statement. Now, the second one, okay, adjusted R-square is non-negative and indicative of the model's out-of-sample predictive power. Is this correct, or do you think that's a false statement? Those who just came in, 5 seconds for you, okay? 5, 4, 3, 2, 1, okay? So this is related back to what we've covered in topic 2 last semester. Now, this is actually a false statement, okay? The entire sentence is completely wrong. First of all, adjusted R-square is not non-negative. Adjusted R-square can take negative values. It's the R-square that is strictly bound by 0 and 1. Adjusted R-square is bounded above by R-square, but it can be negative. Okay, that's the first part that is wrong. And secondly, it doesn't tell us anything about the model's out-of-sample performance. Adjusted R-square, just like R-square, only tells us the proportion of the variation in Y that has been explained by the model. Okay, it's the proportion of the variation in Y, the Y that it's in sample. Okay, we don't know anything about out of sample because that's not how the R-squares are computed. So this is a false statement. Adjusted R-square can be negative. Okay, and it doesn't tell us anything about the model's predictive power. At best, it only tells us the variation in Y that has been explained by the model, adjusted by the number of parameters. Okay, so this is false. So these are the two statements that's related to what we've covered last week. If you find something that you don't understand about the adjusted R-square, okay, it's time to go back to topic 2, the lecture notes on the adjusted R-square part, and review the related part of the lecture notes and slides. So that's chapter 4 for adjusted R-square. Now, coming back to what we're going to discuss today, forecasting. So basically this week we'll cover forecasting, and this is basically applying what we've seen in the first 3 weeks and sort of like more about application and less about theory. And I think this is sort of a lighter week compared to the next 3 weeks ahead, okay? So this week we'll finish on forecasting. The next 2 weeks we'll be discussing some formal detection of non-stationarities, okay, some hypothesis tests that allow us to to formally analyze whether a given data series is stationary or not. And then the very last week before reading week, we'll come back to modeling different time series, okay? Once we have a single time series under control, that will be able to comfortably extend what we've seen to multiple time series, which means I've sort of decided before, sorry, not reading week, the Easter break, what I meant is, okay, before Easter break, we'll just focus on time series, okay? That means the midterm will solely be based on time series, and after the midterm, we'll come back to a fresh start on causal inference. Then we'll be looking at experimental designs, okay? So, because I find it a bit awkward to start a week on causal inference and then we have like 3 or 4 weeks break and then come back to that again. I feel like that's not really nice. So before Easter break, we'll just be focusing on the time series. Now, forecasting, okay. So essentially, forecasting is to use what we observe in that given sample to forecast future values. Okay, so imagine we observed observations starting from t equal to 1 to capital T. So typically, capital T is a very standard notation in time series to indicate the end of sample observation. Okay, so the last observation in the sample. And we want to use it to forecast future values for y capital T plus 1, 2, or whatever value of h one might be interested in. And typically, this h is what we call a forecast horizon. Okay, so it defines how far into the future we want to forecast. So some terminologies. So for h being 1, basically means that you want to forecast the immediate future observation. So that is termed the one step ahead forecast. Okay. For longer term predictions, that's basically h step ahead forecast. So for example, h being 2, that's 2 step ahead forecast. H being 4, that's the 4 step ahead forecast. Okay. So basically just insert the specific value of h into the terminology. So the basic idea here is we want to find an optimal forecast that minimizes the forecast errors, okay? And basically, the sort of optimality will be based on what criterion function you're looking at. And there is infinitely many different types of criterion there. And for this course, and typically, a very common approach is to prioritize what is called the mean squared forecast error, the MSFE. So basically, we attempt to minimize the squared forecast error in expectation sense. That's basically very similar to our minimization problem that we use to establish the regression model. Okay? So the idea is to use the past up to time capital T. So all the information, they are embedded in this curly Y notation. Okay, so whenever you see this curly Y notation with some subscript, okay, basically that subscript tells you up to which time we have information about. So given that, basically we want to find a suitable function, okay, the best functional form of all past history up to time T, regardless of it being linear or non-linear, that optimally forecasts the future in a sense of minimizing the MSFE, okay? So we're minimizing the error, which is given by the future value, the YT plus H, subtracted by the forecast based on the history, okay? And the difference between these two is essentially the forecast error, taking it to the square, and then taking the expectation of the square. And this minimization problem attempts to find the best functional form, okay? So we're minimizing all possible form of the M, which is essentially what we are already really familiar with, okay? The best general prediction problem. It's just that previously it was just for some in-sample data. Here we attempt to minimize the out-of-sample forecast error, okay? So by now you should know that the solution to the best general prediction problem is essentially the conditional expectation, okay? The conditional expectation of YT plus H, given all past history, is the best functional form of the past that best predicts the future in a sense of minimizing the MSFE, okay? And a very typical notation here is that we typically denote the optimal H step ahead forecast and using this notation, okay? So the bar and the T indicates that it's the optimal H step ahead forecast using history up to time capital T. So whenever you see this notation, basically that is just a conditional expectation of the future given the past. So we use this notation to sort of denote this conditional expectation a bit more compactly. Okay? And this is something you should remember. If you're interested in why the conditional expectation emerges as the solution to this problem, you should check back. I think that was homework 2 or homework 3 in semester 1. There was one final question in either homework 2 or homework 3 that a lot of you thought it was very hard, but essentially that was giving you the proof of why conditional expectation is the solution to the best general prediction problem. Okay? But if you're not interested in the derivation, don't bother to check it. But you should really know that this is the result. Okay? Conditional expectation is the best general predictor in the sense of minimizing the mean square forecast error, or in the sense of minimizing the mean square prediction error in our regression case, which we had discussed in topic 1 last semester. Okay? So the specific functional form of this conditional expectation, or so-called the optimal H-step ahead forecast, will then depend on the specific model we attempt to use to describe the underlying data. Okay? If it's an AR model, then the specific functional form of C would then depend on our AR model specification. If it's an MA model, it would then depend on that specific model specification. So we're going to see in a bit that we shall establish our optimal forecast using the AR model. And the difference between the actual future value and the forecast, okay, that is denoted using this E, okay, that's the H-step ahead forecast using information up to time t, and E stands for the forecast error. It's not really an error, okay, it's not a mistake. It's basically the difference, okay? So this error should be understood as a difference, okay? So that's given by the actual value and the optimal forecast we've established using some given model. And we'll come back to the forecast error on Friday. This is related to forecast evaluation, how good the forecast is, given some model specification. So this is the general setup. Now, bringing it back to our AR model, and remember, the AR1 is a descriptive model, but it comes with assumptions, okay? It's a descriptive model with the assumption that we assume the error term U, the shocks, they are IID white noise with mean 0 and variance sigma square U, and that it's independent of all paths of Y, okay? So UT is independent of all paths YT minus 1, YT minus 2, all the way back to the infinite paths. And recall that the immediate consequence of having such a model is that the conditional expectation of YT based on its entire history up to t minus 1 depends solely on the immediate path, YT minus 1. Okay? This is because UT is independent of all past history. So the conditional expectation of UT given all paths is essentially 0. And remember on Friday, we've said that the conditional expectation of the variable given itself is just equal to itself. The best prediction one can make about one variable, if that variable is given, is of course equal to that particular variable. So, okay. So what we have here, the conditional expectation of YT given all past history. If we plug in the AR1 equation, okay, and then next, if we make use of the linearity of expectation, that basically gives you, first of all, the conditional expectation of the intercept given the past information. Intercept is a constant, so it's equal to itself. And then we have the second term, alpha 1, yt minus 1, conditioning on all past history, plus the conditional expectation of ut given all past history of y. Okay? The last term is essentially 0 because, okay, ut is independent of yt minus 1. Given independence, the best we can predict about ut given the past is, of course, 0 because there exists no relationship between them. Now, for the middle term, first of all, alpha 1 is constant. Just take it out, okay? So the middle term is equal to alpha 1 times conditional expectation of yt minus 1 given all past history. Now, everything in the past up to time t minus 1 includes yt minus 1, yt minus 2, yt minus 3, all the way back to the infinite past, which already contains the yt minus 1 that we attempt to find the conditional expectation for. So this is just equal to itself. And taking all these together, okay, that basically implies a conditional expectation of yt given all past history of y is the alpha naught plus the alpha 1 yt minus 1. Okay? This is something by now you should be very familiar with. I've shown the derivation multiple times. Okay? So this is the immediate consequence of the AR1 model assumption, which means, given this, the optimal one-step ahead forecast is essentially takes the same functional form, except that instead of having the lowercase t minus 1, the optimal one-step ahead forecast is based on the last observation in the sample, y capital T. Okay? So if we plug in the model equation for the one-step ahead observation, the yt plus 1, given all past information up to capital T, okay, this is equal to the expectation of the alpha naught, okay, plus alpha 1 multiplied by the immediate past of yt plus 1 is just the y capital T plus the u capital T plus 1, the error term at time t plus 1, okay? You look at the AR1 model, yt has error term ut. Of course, y capital T plus 1 has error term u capital T plus 1. The shock happens at the same time period as the observation appears on the left-hand side of the equation. Okay? This is given y capital T. Then again, alpha naught constant, just take it out. We have the plus alpha 1 expectation of y capital T given all past information up to time capital T. It's already contained inside, okay? Which means the middle conditional expectation must equal to the last observation of the sample itself. Sorry. This is just y capital T, okay? And again, ut plus 1, that's in the future related to all information captured by this curly y. They are independent. So the conditional expectation is just 0, which is why our optimal one-step ahead forecast emerges as alpha naught plus alpha 1 times the last observation in the sample. Okay? Now, In order to compute the optimal one-step ahead forecast, this requires our knowledge of the alpha naught and the alpha 1, which is typically known. Therefore, it's generally not possible to compute the optimal one-step ahead forecast, and instead, we will have to compute the so-called feasible or estimated optimal forecast. This is obtained by plugging in the OLS estimates for the alpha naught and alpha 1, okay? So basically, you just replace the alpha naught and alpha 1 by the sample estimates. Now, one thing you have to be careful here is that this feasible forecast is not a predicted value, okay? This is an out-of-sample prediction. This is an out-of-sample forecast. It differs from the in-sample predicted value that we've considered in semester 1, okay? And this is also for the same reason, there's no such thing as residual in forecasting. We only have forecast errors because residual corresponds to the in-sample difference, whereas forecast error corresponds to the out-of-sample difference, okay? So be careful with the terminology here. So this is the one-step ahead forecast. Now, taking H should be a more general value. So for example, H being greater than 1. Essentially, it's just more like a recursive formulation. So remember, just now we've seen that for H being 1, our one-step ahead forecast depends on the last observation of our sample. Now, when H equals to 2, which is our two-step ahead forecast, then in this case, okay, our optimal two-step ahead forecast, which is again the conditional expectation of yt plus 2 given all past history up to time t. Okay? Now, if we plug in the AR1 equation for y capital T plus 2, that is essentially alpha naught plus alpha 1 times its immediate past, which is y capital T plus 1, plus the error term that happens at the same period as t plus 2, which is u capital T plus 2 conditioning on all past information up to time t. Okay? Now, using linearity again, we have alpha naught plus alpha 1, the expected value of y capital T plus 1 given all past information. And then again, we have the conditional expectation of the error term or the shock given all past. The last term must be 0 given independence, okay? They are independent, so this term is just 0. There's nothing we can forecast about future shocks using the past. Now, the middle conditional expectation is essentially the optimal one-step ahead forecast, okay? Which is what we've already seen, the yt plus 1 given t. So the optimal two-step ahead forecast depends on the optimal one-step ahead forecast, okay? And that's why we have that this is equal to alpha naught plus alpha 1 times the yt plus 1 given t. And then extending this logic, okay, then essentially the optimal three-step ahead forecast is essentially depending on the optimal two-step ahead forecast. So basically what it means is that for any value of h, the optimal H step ahead forecast depends on the optimal H minus 1 step ahead forecast. This basically comes from the formulation of having an AR1 model plus the assumption that we have the error term being IID white noise, and most importantly, the error terms are independent of all past values of y. Okay? That makes the future shocks unpredictable given past. So this is the optimal forecast, okay, H step ahead forecast. And in general, if you assume that if we let H goes to infinity, so as H increases, and if we also have alpha 1 being smaller than 1 in absolute value, which basically means we have a stationary R1, then our optimal forecast would converge to the long-run mean, the expected value of y. Remember, the alpha naught over 1 minus alpha 1 is essentially the long-run expectation. Okay, so the best long-run forecast of a stationary process is its mean. And this is consistent with the fact that stationary process exhibits mean reversion. Okay, remember there was one lecture I showed you, absence of shock. The series will just convert back to its long-run mean. Okay, and given that the fact that all our forecasts, okay, is made without the shock appearing in the equation, then apparently as the forecast horizon increases, our optimal would be long-run mean. You see how you get to prove this formally in the homework this week, okay? So this is the optimal forecast. And essentially, the feasible forecast is just by plugging in the alpha hat, okay? You use the ORS estimates for the parameters, and then you plug in the feasible forecast to replace the optimal ones, okay? So this is the theory. Now, bringing it to the case study that we're familiar with, we've been talking about these two data sets a lot of times, the GDP and the growth rate. Okay? Essentially, the growth rate is the difference GDP. So I've shown you how that was calculated below. I'm not going to talk about it in the lecture, just so that if you're interested in, you should know the GDP growth rate is the difference GDP. That's essentially what defines the growth rate, is how the next period differs from previous period. Okay? And we can see that the GDP is not stationary, whereas the growth rate is stationary. That's our guess. Okay? We have not formally tested this yet. We'll look at how to test this next week. Okay? So, forecasting using the growth rate. So basically, what we have is the data set up to the 1999 Q4, because this is a quarterly data, and we want to use our data to forecast the growth rate in 2000s. So we first estimate the AR1 model, and we can see that, which is similar to what we had before, the alpha hat 1 is 0.29. That is consistent with our guess that the growth rate is stationary. Okay? So the results given here is slightly different from the ones given in the previous slides because I only use a subsample. I sort of truncated that and leave the data correspond to 2000 out for forecast comparison. And what we have is the final observation in this data set, which correspond to Q4 in 1999, is 6.86. Then basically, to compute the feasible one-step ahead forecast, you just plug in the estimated value of alpha naught, 2.45, the estimated value of alpha 1, the 0.29, multiplied by the last observation in the sample, 6.86, that gives you the visible one-step ahead forecast, okay? And similarly, to compute the two-step ahead forecast, that depends on the same alpha hat naught and alpha hat 1, but it relies on the visible one-step ahead forecast. So you could sort of see that there is a recursive nature here. You find the one-step ahead forecast first, and then you insert it to find the two-step ahead forecast. And similarly, that's how you can do for more long-run horizon forecasts. And what I want to show here is if you look at the larger value of h, okay, essentially the long-run optimal forecast gradually nested on, well, sits at 3.45, okay? And essentially, this is showing what we've established on the previous slide, okay? The long-term forecast will converge to the long-run mean, okay? The 3.45 is the estimated long-run mean. If you compute the estimate for mu using the 2.45 and 0.29, okay? So remember, stationary time series, absence of shock, it must revert to its long-run mean and sit there without any attempt to deviate it unless a surprise shock hits the series. So if you look at the graph here, essentially that tells us how our model forecasts the future and compare it to the actual data. So the black lines is basically the same, the actual data series that we've seen earlier, okay? And the red line is also the actual data series for the period that we're forecasting. So we're using the data up to 1999 Q4 to forecast 2000 to 2013 Q4, okay? So basically the red line depicts the actual data for our forecast period, and the blue line inside the shaded area is our forecast trajectory, the forecast value for this period, okay? And the shaded line basically represents the uncertainties. Remember, these are all estimated values. We use the alpha hat naught, we use the alpha hat 1 to compute the visible forecast. Anything that are estimated must come with estimation error, and we can actually calculate the confidence interval. So basically, the shaded area represents the confidence interval. So the first thing that we should take away from here is we can see that, okay, it's just that at the beginning, the forecast value, okay, following a deviation from the mean at the period 1999 Q4, then absence of shock, the forecast value will be driven back to its long-run mean. And we can see this is the reason why eventually the forecast value just stays on that line. This blue line is the estimated long-run mean we calculated on the previous slide. And we can see that the forecast values, they're just a line, okay? It doesn't really capture the variation, the peaks or the troughs, or really closely follow the actual data, okay? The actual data, the fluctuations, a lot of them were actually coming from shocks, especially if you look at the troughs here at the bottom, which is very close to 2008. That basically represent the shock coming from the credit crunch. Of course, when you're back in 1999 Q4, one would never know that there will be credit crunch happening in 2008, and therefore your forecast would never be able to take such a shock into account. So the forecast value is always very smooth. But this is also the fact that we're only forecasting using a very simple model, the AR1. okay? So we can see that the point estimate, so essentially the values given by the blue line doesn't really capture well the actual series. And basically, the blue line is just regressing back to long-run mean value. Now, another thing we have to take into account is that there are uncertainties associated with our forecasts, okay? If you take the shaded area into account, we can see that most of the actual series actually lies inside the shaded area, okay? So even though the point estimate doesn't really capture the actual series well, if we take uncertainty account, okay, the forecast actually generally aligns with the actual series within a certain level of uncertainty. Okay. So this is forecasting with stationary time series. Now, what happens if we forecast with non-stationary time series? And this is also very important why we need to distinguish between a stationary and non-stationary one. So we call that the GDP. It's highly likely to be a non-stationary one given that the estimated alpha 1 is very close to unity. And immediately we can see that the forecast performance is very different for a non-stationary compared to a stationary one. First of all, we can see that the red line, it's getting further and further away from the shaded area as the forecast horizon increases. And most of the red line doesn't actually fall within the shaded area. Now, this is actually getting more amplified if we extend the forecasting horizon, okay? So here I sort of make the forecasting horizon longer just for you to see the more obvious characteristics of using non-stationary time series to do forecasting. So first of all, we can see that different from the stationary one, the shaded area, okay, is getting larger and larger as H increases, which means that there is increasing uncertainty with our forecast, contrast to the previous stationary case. And we can also see that the red line and the blue line, the difference is getting larger and larger, which means the forecast error is growing unboundedly, and this would lead to the forecast variance to grow unboundedly as well. So this sort of illustrates the danger of attempting to use non-stationary data to do forecasting, okay? So whenever we want to do forecasting, given non-stationary time series, we should first attempt to stabilize it. We should convert the non-stationary time series to a stationary one. So here, we can convert the GDP, the non-stationary series, to a stationary one, the growth rate. We've seen that the GDP growth rate is actually stationary. So we should attempt to do forecasting using the growth rate, not the GDP itself. So this is the forecasting with an AR1 model. I'm not going to cover the rest, okay? There are just 2 more slides here on forecasting with higher order AR models. This is basically extending what we've discussed. And it should be quite intuitive, given I've sort of detailed the derivation and the explanation for the AR1. So you should read this after the lecture yourself. Okay, on Friday, I'm going to start on forecast evaluation. Now, not done yet. I want to spend the last 5 minutes to talk about question 3 of the quiz 1. So that particular question is related to hypothesis testing. And to be honest, I thought it was one of the simplest one out of the 5. And I was expecting at least 60 or 70% would be able to get it. But that question has the lowest success rate. Okay, it only 14% managed to get that question correct. Whereas the rest, at least we have like a 50% success rate. So that question, okay, it seems to be the one that a lot of you find it either confusing or find it difficult. But this is nothing new, okay? Basically, that's built upon what you've seen in advanced stats, and we've talked about them in topic 2. So I thought that I should give it another go during the lecture. Next time, I'm gonna ask another similar question in some future quizzes. And I'll be very sad if after going through it during the lecture, you still won't be able to get a success rate like 70%, okay? Now, if you didn't scan the QR code, scan it now. Okay, now coming back to the Padlet question. The next statement, a t-value of 2.5 suggests that the null hypothesis of no statistical significance in favor of a lower-tailed alternative hypothesis at conventional significance levels. Do you think this is correct or wrong? So what it means is if we attempt to test the hypothesis that, let's say, beta 1 is equal to 0 against the alternative beta 1 is less than 0, with a t-statistic that is 2.5, do we reject the null? Okay, quite a balanced vote. So first of all, given we have a positive value, can it ever be possible that we would reject the null in favor of a negative hypothesis? So if we, under the null hypothesis, we know that our test statistic follows a standard normal distribution. A t-value being 2.5 means that it lies somewhere here. Okay. If we attempt to reject the null hypothesis in favor of a lower tail alternative, where should the test statistic lie? It should, of course, lie in the lower tail, okay? For this is the whatever critical value it is, let it be 1.64 minus 1.64 or anything, okay? In any case, your test statistic has to lie in the lower tail for us to enable us to reject the null hypothesis in favor of a negative one, okay? We have a alternative hypothesis that this is smaller than 0. And we know that the standard normal is symmetric around 0. A positive test statistic can never lead to the rejection of the null hypothesis in favor of a negative hypothesis. Okay? Even without attempting to find the critical values, you should know that this is a false statement. Okay? So this is not correct. Now, the next one. A t-statistic of 0.2 suggests that at conventional significance levels, we are likely to fail to reject the null hypothesis, regardless of whether the alternative hypothesis specifies a two-sided or one-sided one. Okay, so basically what we're saying is, given this is our null, regardless of we have being different from 0, smaller than 0, or greater than 0, given a t-statistic of 0.2, okay, we would always fail to reject. Do you think this is correct or wrong? This is correct, okay? Again, coming back to the standard normal distribution. A t-statistic being 0.2 means that it's very small, okay? A small t-statistic will indicate that we are very unlikely to reject the null hypothesis that it's been 0, okay? Think about it. A two-sided alternative implies we have to look at both the upper and the lower tail. The lowest tail test require we looking at the lower tail. The upper tail test require we looking at the upper tail. Something being this small, 0.2, okay? It cannot be greater than our conventional critical values, 1.96, 1.64, or even 2.1, okay? Then again, by computing the t-statistic, we know that it's with this value. Without comparing to critical values, we know that we should fail to reject the null. And this is the two statements about the hypothesis, okay? If you did compute the test statistic for testing alpha 1 being 0.3, you will know that regardless of which data set you're looking at, the t-statistic is barely 0.2 or 0.3, which means we'll fail to reject the null. Whereas, okay, for the hypothesis on the immediate past has no significant influence on current observation. For both data sets, the t-statistic has a value of roughly 2 point something. They're both positive. We will not reject the null against a negative hypothesis, okay? So this is a correct statement. Now, the very last one, before I let you go. The p-value gives the probability of observing a test statistic that is at least as extreme as the one observed in the given sample. You've seen this multiple times in semester 1. Can this be correct? Okay. This cannot be correct, okay? This statement is